Hello, everybody. So we start now with the session focused today on dark matter. We have two speakers, Gaia Lanfranchi and Francesca Calore. Before starting with the first speaker, let me remember you that if you want to do any questions, you cannot do it using the microphone. So please send your questions through the web. In your panel, you have a place to write questions. And in that way, we can read the questions and the speaker can answer at the end of the talk, okay? So let's start with the first speaker. As I said, is Gaia Lanfranchi, and she's talking about dark matter search in accelerators and beyond. Please, Gaia.
Yes, thank you so much. Thank you so much for the kind words and the kind invitation. I would have loved to be in Valencia. Still, I'm very happy to be here. And in particular, because this is not my community. And I think that in these times in which we don't have theory prior for guiding experimental research, we have to cross-talk across community in order to find a way to find something either at accelerator or direct detection or indirect detection. So my topic is how to search dark matter at accelerators and beyond. And certainly this is not the audience where I need to remind how large is the range in which dark matter could sit, more than 80 orders of magnitude in mass. Still is remarkable how the range that allows for a thermalization of the dark matter with the standard model, but sometimes in the early universe is quite narrow, and the ranges between MeV to about 100 TeV scale, and a large fraction of this range can be in fact be explored at accelerator-based experiments. That is what interest, but in particular, I want to talk today about a range that is traditionally less explored, which is the range between MeV and few GeV dark matter, and taking apart for the moment the standard WIMP searches that clearly still a very lively field, but they somehow dominated the scene for more than 1 decade right now, and now the search is focusing on the light part of this mass range, MeV, few GeV, which is, by the way, the range of the familiar matter, so electron and proton, and will be the focus of this talk. So why we like the equilibrium? I think that the equilibrium is a very interesting, important driving principle for searching for dark matter. During the equilibrium, the initial conditions are known, and so this means that they are independent of unknown high energy scales, as we could have in other kind of dark matter models. We have a clear target relic abundance target, and typically this is defined by the mass and the couplings that define the interaction with dark matter and standard model particles, and this is the only known number that we know about dark matter, as you can see here. And the equilibrium is generic and easy to achieve in a very broad, large class of models. So you can imagine a Lagrangian with a 4 fermion effective interaction with the standard model fermions interacting with the dark matter with a sort of mediator. And the condition of reaching an equilibrium also set the scale of the couplings that are at play in this kind of context, that you see that for lambda, which is typically the scale of the mediator and the mass of the dark matter at the level of the GeV, are quite tiny couplings. So we are discussing about feebly interacting particles in that sense. You know, because you probably have heard the beautiful talk by Joni Tockberg a couple of days ago, that now the interest also in the direct detection dark matter is moving in the low range of the direct detection, so below a few GeV, where new technologies are allowing to push the limit down to the neutrino floor. And this is the new frontier, if you want, while the WIMP frontier clearly still alive and is producing and will produce in the coming decade very interesting results. But this is the real new frontier. And this is exactly what we can explore also at accelerators. How we do that? This is a simple sketch to show how we do that. Clearly, in direct detection experiments, you are looking for the scattering of dark matter with respect to some standard model particles. At accelerator, we hope to produce mediators by standard model particle interactions, either at colliders or at beam dump or fixed target, and we hope to see a mediator decaying either in dark matter or again in standard model particles, depending on the mass hierarchy between the mediator and the dark matter particle. Clearly, all these should be compared against what we know from cosmology, so the relic density that we know in the universe, which is the only currently known number we know about dark matter, and the cross section clearly can be expressed in terms of basic parameters of the theory that typically are summarized by the mass of the dark matter, the mass of the mediator, the coupling of the dark matter with the mediator, and the coupling of the mediator with the standard model. So somehow a theoretical framework is key in order to interpret the results and compare them across different fields, not only within the accelerator communities, but also towards other communities like direct detection and indirect detection. Another important point that I want to underline with respect to the direct detection realm is that the range of the momentum transfer of a putative dark matter particle with the standard model. So at direct detection experiments, typically the momentum transfer is very small with respect to the mass of the dark matter particle, and therefore the interaction is much more sensitive to the detail. The scattering is much more sensitive to the detail of the interaction. While at the accelerator case, we are in the opposite extreme of the scale, where the momentum transfer is far larger than the mass at play, and that is why we are less sensitive to the details of the interaction, and somehow this is a strength, if you want, of this approach. This clearly reflects in a huge difference in terms of relic target, because as you can see in this plot, this is a well-known plot from an important community report that was published in 2017 in the US, where you see the different relic targets depending on the nature of the dark matter particles. They spread over several something like 20 orders of magnitude in the case of direct detection experiments, just because of what I said, because direct detection are more sensitive to the details of the interaction, while in the case of the accelerator experiments, they are more clustered in a very narrow range of the parameter space. So this is very important. So what we are doing now, the accelerators, let me concentrate first of all at CERN. CERN is moving towards this field quite recently. It was not in the core business, but now also triggered by the lively activity that we see emerging in the direct detection community. We are starting a sort of search, somehow structured search of light dark matter between MEV and the few GV. And the optimal way to do that is to do not at collider, because the collider is very high energy, but rather at extracted beam lines. And we are lucky because CERN, by the north area, can provide a large variety of extracted beam lines, protons of 400 GeV, electrons of 100 GeV, muons with a range between 100 and 160 GeV, that can be used to test several models, depending also the typology of the coupling that the dark matter could have with the standard models. There is not only that, there is a sort of blooming field also at colliders, but in a sort of non-standard detectors that are being proposed at the interaction points, but very far away from the interaction point, so very different geometry with respect to the standard experiments, because they want to profit of the fact that, as I told you, we are dealing with feebly interacting particles, so very small couplings, and therefore typically long-lived particle living on a macroscopic scale. And that is why we need the detectors that are placed very far away from the interaction point. Clearly, CERN is only one of the players in the game, in the accelerator realm, to search for this light dark matter. Essentially, all the major laboratories in the world are approaching this challenge. FNAL, SLAC, JLab, Keck, Mainz, Frascati, JPark. And you see different experiments either existing or proposed with different techniques, different beam lines that will try to cover different regions of parameter spaces I'm going to show you in a moment. So, how to guide accelerator-based experiments and interpret the results. Clearly, here is somehow in the light dark matter realm we are new, and we need a theoretical phenomenological framework in order to guide the experimental effort, to extract from the searches meaningful information, and also to compare results not only across our community but also against direct detection and direct detection. This is clearly a worldwide effort. It's not only related to CERN, but CERN recently, after the outcome of the European Strategy for Particle Physics, decided to set up a body that should study the problem. And this body is the new Feebly Interacting Particle Physics Center of the Physics Beyond Colliders activity that is collecting among several theorists very known in the field. So this is the structure of the Physics Beyond Colliders activity. We have a different experimental facility. I have no time to enter in detail, but essentially this center should somehow act as a central forum to assess the physics reach of different proposals and experiments, also as far as light dark matter is concerned, and put them in a worldwide context to understand if an experiment is competitive or not. So we are organizing the work in three main directions. I think all of the three are relevant for this community. We have the light dark matter, so MeV, 10 GeV, the ultralight Feebly interacting particles, so this is essentially spanning the axion realm, ultralight object, it can be also dark matter component, and a direction that is more studying the possibility to have a retarded neutrino in the low CISO models, low scale CISO models, but this is beyond this conference. Today I will concentrate, of course, on the work that we are doing in this context of the light dark matter between MeV and 10 GeV, let's say, where the synergy with direct and direct detection is the strongest. So these are the names of the current member of the Physics Center. You can recognize here renowned people from the theory side, always a light dark matter in the accelerator realm, Philip Schuster, Gordon Kmianic. We have a representative of the direct detection dark matter, Jocelyn Morrow. We have a representative from the LAC dark matter working group, Philip Harris, and many others. And Maxime Pospelov gave the talk at this conference 2 days ago, is the leading theorist, and I'm acting as the contact person for the experiments. So which is the approach, clearly? So clearly, this was the initial discussion, which approach we should have in order to guide the experimental searches towards this direction. Top down, maybe. Bottom up, that means essentially base the searches only on signature without having any prior. This is also has pros and cons. We decide to do both. And in doing both means that we want to define benchmarks, theory benchmarks that are not specifically linked at specific model, but are rather representatives of large classes of models. And if the dark matter, so just to give you an idea how we are pursuing the reasoning, we know that the dark matter, if it was in equilibrium, the early universe has to interact with the standard model because its abundance has to be depleted by some mechanisms. Otherwise, either would be too hot for large scale structure formation or would require a standard cosmology. So we will see in a moment how this could happen. And what we know also is that if we are looking for sub-GeV dark matter, this has to interact with standard model with new forces, because if it would interact with weak, electroweak forces, this would violate the Lie-Weinberg bound. So would not be possible to recover the relic abundance. Moreover, dark matter standard model mediators should be standard model neutral, because otherwise would be already discovered at past and current colliders. We know also that for S-wave annihilating dark matter, the measurement of CMB rule out masses below the 10 GeV. So if we want to look for dark matter below 10 GeV, we have to consider dark matter in P-wave. such that the relative abundance is depleted as soon as essentially the temperatures goes down, so the universe expands. So if we start from the first point, the new forces and the standard model neutral operator, this is a kind of top-down approach, but you see that it's somehow a lively interplay between top-down and bottom-up. We ending up with the lowest dimension operator of dimension 4, only with 3 possibilities. We have a vector portal, a scalar portal, or a fermion portal. Among these 3, only the first 2 allows for a thermalization, because the fermion portal would allow coupling too tiny to produce thermal dark matter in the early universe. So for today, we discussed these 2 that are somehow currently driving our searches. How to produce vector mediator? If we are in the vector portal, but the vector mediator is linked with a photon. And whenever you produce a photon, you produce possibly also vector mediator by kinetic mixing. So this can happen by Bremsstrahlung, can happen by decays of light mesons, can happen by A+, E- annihilation, or proton-proton collision for sure. For the scalar mediator is a bit more tricky because you can produce a scalar whenever you produce an X, either off shell or on shell. And the X can be produced, for example, off shell at the extracted beamlines whenever you have a decay of B and K kaon. Via again a kinetic mixing, you can produce a scalar that then can possibly decay in standard model particles. Clearly different signature as expected depending on the mass hierarchy between mediator and dark matter. And at the accelerator-based experiment, in particular at extracted beamlines, we have different experiments targeting different range of dark matter and mediator's hierarchy. So for a mediator less than the 2 dark matter mass threshold, the mediator will go back to standard model particles. And this is the kind of WIMP searches that is used currently by this list of experiments or proposals. If the mediator instead is above the threshold, so it can produce 2 dark matter particles, the dark matter can either scatter with the medium of the detector or be detected as a missing energy or missing mass or missing momentum in the overall kinematics of the event. And these are techniques that are used by different experiments that I have no time to describe in detail, but you find all the details in the report I told you at the beginning. At accelerators, clearly, you can produce dark matter in several ways, and you have at the moment 2 colliders running, the 2 experiments, so BEL2 at the Y4S, and BES3, in reality so they are 3, at the BEP-C2, and then clearly the standard LAC detectors. Here again, depending on the mass hierarchy between dark matter and mediator, you may have bump searches. So look for peaks over a smooth background if the mediator goes to standard model particles, or missing mass or missing energy. So the mediator mass hierarchy also define how dark matter annihilates in the early universe into standard model particles, clearly, because if the mediator is above the 2 dark matter threshold, then you might have the direct annihilation, and this allows us to have a clear Rayleigh target, because when we measure standard model particles at the final state, we are sensitive to somehow this coupling here that can be related with initial abundance. If instead we are a mediator whose mass is below the threshold of 2 dark matter, you have in this case a hidden or secluded annihilation, where the mediator, once created, goes back to standard model particle. In that case, you lose the connection with the Rayleigh density. So let's focus on the first case that maybe is the more interesting. And here you see different topologies depending on the portal that you consider. And but we have other constraints coming this time from cosmology, and the dark matter below 10 GeV we saw before, if it is annihilating S waves, is excluded by CMB. And this is well known by the experts in the field. And so we need to find a way to annihilate dark matter in more, if you want, to freeze out dark matter. And this can be due to the fact that dark matter is created in P wave. And because in this case, you deplete the density essentially as long as the temperature goes down, the velocity redshift with as far as the universe expands. So in that case, you have all these three possibilities, and we start with that, scalar dark matter into a vector mediator. For that, we have a model where we can write down in a clear way, which could be the cross-section at accelerator, the cross-section at direct detection, and how to compare it with cosmological relic abundance. In that sense, the work that we are doing is to take, for example, this benchmark and to put on the same plot the sensitivity that we get from different experimental proposals or experiments. You see here in filled area the experiments, the current bounds, and in the lines only expectation from future proposal. And compare also with the relic density for this particular case. So you see here belt 2 compared against the electron beam dump, proton beam dump, and future fixed target experiments, for example, as LAPTH. The interesting part of this plot is that within this framework now we can compare with direct detection, and this is the super CDMS line that you can find also in the typical plot of cross-section spin independent nucleon cross-section. And so you have a framework where you can put the limits one on top of the others. The same is true, for example, for Sensei, which is driving, if you want, the searches in the low mass range of the dark matter that can be compared one-to-one with other experiments, accelerator-based experiments, for example, LDMX or SHIP in the future, or BEL2. If the dark matter is, instead of being scalar type, is a Majorana pseudo-Dirac, then in that case, the accelerator experiments would see a signal, while the dark matter direct detection experiment would see nothing, because the splitting would be such that essentially the scattering is quenched off, and so you see nothing. And this is a typical example that is typically presented to show the synergy of the two approaches. The two approaches are complementary, synergistic, of course, and depending on the model, one is sensitive, the other is not, and vice versa. If both are sensitive, this is the best case, because they can complement each other in terms, of course, of information. Last but not least is the scalar mediator with a fermion dark matter. Even in this case, we have the projection and the actual bound from accelerator-based experiments, where we see, however, that for S-channel P-wave annihilation, essentially we have already saturated the relic density. So here, in principle, this model cannot explain in its entirety the dark matter abundance, at least below 10 GeV, of course. And this is also an interesting example to compare with the LAC results that are using, for example, the same framework, scalar mediator, fermion dark matter. But you see that there is a discrepancy between the communities. I would say this is somehow mostly driven by the extracted beam lines. This is mostly driven by proton-proton colliders. They use the same model, but very different couplings. And now we are working towards having a sort of a set of coupling which are a benchmark for both. So I would say that first, so essentially it would be very interesting to see how the sensitivity of the LAC and future projection would go by the coupling decreasing. So this already we know qualitatively that would go up, but quantitatively this should be worked out. Clearly, this does not apply in the case of the invisible X-width. That is one of the most powerful way of searching for dark matter at the LAC, because it does not imply any assumption on the strength of the coupling. However, clearly the limitation is that this is a model valid only if the mediator is the X. Clearly, is not extensible immediately to other scalar mediators. Last but not least, let's conclude by saying that what happens if the mediator is below the threshold of the 2 dark matter mass. In that sense, we don't have any relic target, relic density to target, because as I told you, essentially we are sensitive only to a parameter that we cannot measure, at least in the accelerator-based experiments. In this case, we are sensitive to the mediator decaying back to standard model particles. This is what I explained to you at the beginning, the bump search. So we're searching for a bump, a peak over a smooth background. And here you see that there is a very lively activity, both at extracted beam lines that you see here, essentially in this part of the plot, and the colliders, WIMP2, CMS, you see LACB, and others, PABAR, that typically are more sensitive towards larger mass and smaller and higher coupling, larger coupling, while the extracted beam lines are exploring lower mass that are essentially the range we are discussing here today, and very low couplings, I would say 10 to the minus 5, 10 to the minus 6, 10 to the minus 7 is the typical coupling we are considering. This is the case also for the scalar case. So if you have a scalar mediator going to visible final state, again, even in this case, we have a very interesting activity. We have an upper bound set by the Higgs invisible width in case the scalar is the Higgs. And several projections coming, in this case in particular, from the detectors put far away from the interaction points of the LEC. But you have also been damp like NA62, Dark West, FNAL, and BEL2, as you can see. Clearly, very important are the boundaries coming from astrophysics and Astroparticle, the supernova, and the BBN. So take a breath, and these are my conclusions. Also are an outlook for the field. In these 25 minutes, I hope I have to convince you that accelerator-based experiments have unique potential to explore the light dark matter range, and they can perform a comprehensive sensitivity study in this range, assuming that this is a thermal relic from the early universe. Fixed target experiments we are already seeing are complementing proton-proton collider in the low mass range, where they are typically much more sensitive, just because they are working at much lower energy, so they can afford to detect very light objects. Still, as you have seen, we have inconsistency between the two communities that we are trying to fix, and we are trying to agree upon a common set of benchmarks to really benchmark one another. We see obvious strong complementarity and synergy with the direct detection in the same mass range, because clearly no accelerator-based experiments will never tell us if what we detect is cosmologically stable. This we need the direct detection experiments to tell us. And I would say also that the complementarity with the indirect detection is currently missing, and I'm very happy that Francesca will give the talk right after me, because I think we have to find a common point to work together. We are trying to set up a common set of benchmarks. You can find the full list of results. All the plots I've shown in this talk come from this work. More you can find in this website. More will come in the future and will be posted in the same website. And we are trying to set up a framework that could guide new proposals also towards uncharted regions of the parameter space, in order not to waste time and money. Last but not least, crosstalk across different communities, and that is why I'm very happy to be here, is difficult, but I think that is compulsory now that we don't have a strong theory bias. We will try to have a first go in this framework, and strict collaboration with the direct detection, astro and cosmo communities, I think will be key and will be more and more sought for the future. With that, I thank you for your attention.
Okay, thank you, Gaia, for this very nice review. If there are any questions, I don't see clearly any. So I have a question concerning, because you mentioned very fast the issue of the, for example, the direct detection experiments like super CDMS. No? Could you show again the transparency and explain a little bit more how is the comparison with
yes
accelerators and versus?
Yes. Yes. So essentially, the framework. So first of all, in order to make properly this comparison, you have to adopt a framework, and the framework we are discussing here is a vector mediator with this elastic scalar dark matter. Okay. Within this framework, we have essentially 4 free parameters. That is the coupling of the mediator with the standard model, the coupling of the mediator with the dark matter, and the 2 masses that are unknown. If you fix with reasonable assumption 2 of the 4, then you can plot this variable y as a function of the mass of the dark matter you are assuming, is not that you are scanning, and this variable y is made of a combination of variables that you can have also when you have direct detection. That is why I put explicitly the formula. So you can recombine this variable in this framework, and that is why you have a one-to-one conversion between the spin-independent dark matter nuclear cross-section that depends on these parameters and what we see at accelerators, which is y versus m key. And the same holds for Sensei, of course, but also for others framework. For example, the Majorana of pseudo-Dirac. In this case, you don't have in principle signals for direct detection because you have this mass splitting of the dark matter that do not allow you to see a signal, but you have a one-to-one comparison in case you would be able. And the same is true for all the benchmark I explained you. Clearly, they are valid within a given framework, which should be clearly spelled out. On the other hand, they are representative of broad classes of models, and they are fully compatible with what we know from astroparticle, from cosmology, also from quantum field theory, from the Lagrangian of the standard model. We don't put by hand the terms that could create divergence in the ultraviolet, for example, are all terms that are well behaving also from a mathematical point of view, so could be very easily embedded in the structure of the standard model. Mm-hmm. This is clearly a work in progress. This is just the first step. And that is why we have so many theorists in the committee also, in order to avoid to make mistake, and also to be driven towards the solution that are starting from the more simple, we move on towards more complicated solution. But this is somehow is the idea.
Okay, thank you very much for this nice explanation. So we have already finished with this first talk because it's already 3 o'clock. So we have to go to the next talks. Thank you very much again, Gaia, for this very nice review.
Thank you. Thank you.
So let's go for the next speaker, which is Francesca Calore. And she's going to talk about indirect detection of dark matter. And again, if you want to send questions, please do it through the web. Please, Francesca.
Thank you. So good afternoon, everyone, and thanks a lot for the kind invitation and for the possibility to present here an overview of indirect detection of dark matter. So as we have seen already, the landscape for dark matter candidates is broad, not only in the mass interval that dark matter candidate can span, but also interaction strength. And depending on the mass range, but also on the phenomenological implications that different candidates may have, we can classify several candidates based on their properties. Whenever you want to engage in some kind of identification strategies, then you have to be somehow more or less model dependent. And this is why there is always a kind of theoretical prejudice in dark matter searches, which is set on the one hand by what you can probe with available data, and on the other hand, on what are the phenomenological signatures of your model. And based on that, indirect dark matter detection relies on what dark matter does, so how dark matter interacts with the environment. You can have and classify several mechanisms and study several candidates in this way. So the first principle is to have dark matter that can inject particles or energy into the medium, and this holds for the well-known weakly interacting massing candidates, but also for other type of dark matter candidates such as primordial black holes. You can also have dark matter to be felt by standard model structures in astrophysical systems and leading to observable signatures through gravitational interactions. And finally, you can rely on the fact that dark matter particles or dark matter candidates can interact, being captured or scattered off different astrophysical objects, starting from stars, going to more dense environment like neutron stars and black holes, and exploit the signatures that would come out from this kind of mechanisms. So if we want to classify dark matter from a different perspective, what we can do is to look at the astroparticle observables that can leverage our knowledge of dark matter. So here is just a summary of the different observables through which we can try to study the nature of dark matter and really explore the full mass range. So starting from what we can do with cosmic surveys and more local measurements of the dark matter densities, this can probe either very light dark matter particles or macro objects such primordial black holes. And survey science is something that is really flourishing right now and in the future even more, that will allow precision measurement of the dark matter density at different scales and test the cold and collisionless hypothesis for dark matter. It can also constrain interaction of dark matter with the visible sector, as it has been probed with a sensitivity prediction for the Vera Rubin observatories. And based on the difference in the properties of the large-scale structures that will be formed through driven by different dark matter candidates, one can actually set limits on very light dark matter candidates, which would actually impinge some wavelength effects in the structure formation. It will also be possible to study and measure the dark matter clustering and even the presence of dark matter subcomponents at the percent level with measurements related of intensity mapping in the late universe. Another way to probe dark matter through gravitational interaction is thanks to gravitational lensing, and in particular in macro lensings that can set constraints on compact objects, and in particular on the fraction of compact objects that could make the dark matter in the universe. And this has been used to set constraints on primordial black holes, axion mini clusters, ultra-compact mini halos, and also boson stars. And if we focus on primordial black holes, microlensing constraints are sensitive to primordial black holes down to 10 to the 22 grams per mass, while there is a interval in mass between 10 to the 17 grams and 10 to the 22 grams, which is the so-called asteroid mass, which remains completely unexplored. And this can be actually closed up in the future through the observation of lensing parallax and femtolensing of gamma ray burst. While on the other hand, microlensing can be pushed down perhaps to 10 to the 21 grams with the Raman space telescopes and also the Vera Rubin Observatory. However, there are also still effects that needs to be worked out theoretically in order to fully exploit the powerful of data, and in particular the wave-optic effects and the effect of source finite size. Coming to traveling messengers, those offer actually a way to probe and explore a very broad range in mass and candidates through the different cosmic radiations, different wavelengths, and the cosmic microwave background power spectrum and spectral distortions. So let me start with the possibility that we get narrow line signals from dark matter decaying at energy scales that are of the order of the dark matter mass. And this happens whenever you have a light dark matter candidate below the electron mass. So in this case, for example, for candidates of axion and axion-like particles in particular, you can have narrow line emissions from radio up to X-rays, that you can look for with several dedicated experiments and also radio telescopes. But axion and axion-like particles would also induce monochromatic radio emission in the megahertz and gigahertz band, thanks to the conversion in very highly magnetized environments, like a resonance conversion in neutron stars or white dwarfs, and no resonant transition in other type of astrophysical objects, such as stellar winds. Perhaps the most prototypical example of line signals from dark matter candidates is the search for X-ray lines for TeV to MeV sterile neutrinos that can really be probed with future X-ray satellite and telescopes, as for example the upcoming Altina telescope. If we then go up in mass, we open up several channels for producing a continuum emission that is centered at an energy of the order of the dark matter mass. This can go through dark matter annihilating or decay into standard model particles, which are not stable but rapidly decay and hadronize in a flux of observable particles that we can target with current telescopes. As an example of the partition of a particle distribution for dark matter annihilating into big quarks, we see that photons at GeV energies for a mass of 200 GeV can be produced, as well as final observable electron and positrons, but also neutrinos. And the energy distribution of those final products is engaged by this term, which is the energy spectrum of the signal, while the full emission, so if we also want to take into account the spatial distribution of the expected signal, for example, for gamma rays, depends on the density of the dark matter squared along the line of sight, if we take the example of dark matter annihilation. So in this case, we can really have a full expectation of what is the different products that comes from dark matter particle emission. On top of this, whenever you have emission into prompt photons, as I've shown you before, you also have secondary particles which are produced, and those interact with the environments. And in particular, electronic particles can undergo different mechanisms like inverse Compton scattering and synchrotron emission, leading to a truly multi-wavelength spectrum. So you will get a peak from inverse Compton at X-ray energies for a typical dark matter annihilating to be quarks 100 GeV, but also you would get synchrotron emission at in the gigahertz band, so explored by radio telescope. And so you can really leverage on this multi-wavelength spectrum in order to look for a WIMP dark matter signal. So what is then the allowed window for WIMP particles and how we can probe it? So low masses, as also Gaia was showing, are actually very well constrained by the cosmic microwave background, while at higher energies and higher masses are gamma ray telescopes, either on the ground or in space, that leads to the strongest constraints. And indirect detection can offer you a unique way to make a link directly with the thermal relic and the production in the early universe of dark matter, in order to interpret the data in a consistent and conservative generic model. And this holds for WIMPs, but also for other kinds of models. So whenever you want to engage in searches for WIMPs in gamma rays, if you want to focus on that, then you have to define what is your target of interest, and to choose the targets, it's always a subtle balance between what is the signal expected from a given direction and what is actually the background that is affecting the search. So while the galactic center is perhaps the most promising place to look for dark matter because of the very peaked profile, then other places like dwarf spheroidal galaxies offer you promising targets for detection and surely strong targets for constraining dark matter. So the current status on WIMP annihilating constraints has been also presented in this conference before, but is given for GeV masses by the combined constraints from the null observation of photons from dwarf spheroidal galaxies, which also combine different experiments for the first time and actually exclude thermal WIMPs below 100-200 GeV. If we want to push our eyes to a TV dark matter candidates, then the strongest constraints comes to a very deep observation of the galactic center with the S atmospheric Cherenkov telescope, and which is really challenging the thermal dark matter hypothesis at TV scale. In the future, how the limits from dwarf will improve will not only depends on how many more Fermilab data we can collect, but above all on how many new dwarfs future optical surveys like the Rubin Observatory will be able to discover. And then this can set very competitive constraints, which will be also complemented by radio and X-ray observations. On the other hand, there are other targets, and how the limits from other targets will improve will depend on our ability of controlling background theoretical systematics. Having robust limits on dark matter annihilation in the GeV to TeV range will also allow us to test putative signals, like, for example, the interpretation of the GeV excess in terms of dark matter. This was a signal seen in the data of the Fermilab, which seems now mostly being of stellar origin, although a debate is still ongoing. And finally, complementary techniques and multi-wavelength searches will be required to truly test the excess nature and eventually unveil the origin of dark matter. If we want then to explore other energy ranges, we can go down to MEV energies, and this will hopefully be something that will be realized in the future, covering what is called the MEV gap, where we do not have any instruments besides integral and Comptel, and we hope to cover this very interesting energy range with future mission, which have been proposed and can really be of importance not only for low dark matter candidates, but also for astrophysical studies. On the other hand of this energy range, the TV frontier is something that is already explored thanks to the great results of TAUP, LASO, and T-beta IS gamma, which has also been presented here, and for which great wealth of data will be expected in the future. And complementary to that, we will have SWGO and most importantly, the Cherenkov telescope array, which will have a sensitivity of dark matter. We push down to touching the thermal expectation for dark matter at the TV scale through what will be the galactic center survey. But high energy emission and will not only probe WIMP dark matter particle candidates, but can also probe primordial black holes. And indeed, very light primordial black holes can be evaporating today and inject charged cosmic rays and photo via Hawking radiation through an almost black body emission, which will have a temperature inversely proportional to the mass of the primordial black hole. And in this way, the observation of the extragalactic gamma ray and X-ray backgrounds on the one hand through the photon contribution, and on the other hand, the observation of electron and positron fluxes from Voyager and Integral can set very strong constraints on the abundance of PBH in the universe today for masses below 10 to the 17 grams. In the future, it would be again compelling to have an MEV instruments able to measure the gamma ray and X-ray backgrounds, and perhaps reaching up 10 to the 18 gram to close up this mass window. On the other hand of the mass spectrum, also heavy primordial black holes in the range of 10 to 100 solar masses can be constrained by high energy astrophysical emissions, because those primordial black holes, as it occurs for normal astrophysical black holes, can accrete gas and induce observable X-ray and radio emission, which we can look for in catalogs of X-ray and radio observations. This same mechanism also is at play in the early universe, and constraints can be set by looking at the CMB spectrum. However, there are still theoretical uncertainties, for example, on the details of the accretion rate and ionizing effects of the radiation, which affects actually the robustness of those kind of limits. And future radio facilities like SKA and NGBLA will turn very important to set strong constraints on the PBH abundance and eventually unveil a population of PBH at the galactic center. So in order to conclude this review on indirect dark matter detection, let me also mention that in the very recent years, the study of how we can constrain dark matter through gravitational waves and compact objects has been very much developed through different studies. So there have been also some very exhaustive reviews about how we can use gravitational wave to constrain dark matter at different levels. So we can constrain primordial black holes through either the imprint that they would leave in the stochastic gravitational wave background, depending also on the formation scenarios that they may undergo, or in the signatures in the LIGO-Virgo band that would be induced by binary PBH mergers. We can have gravitational waves induced by environmental effects that I will discuss briefly after, that can really emerge whenever dark matter particle candidates interacts with strong density and gravity environments. Other type of searches relying on gravitational waves can set limits on exotic compact objects when dark matter may form new binary systems, especially with very promising detection sensitivities perspectives in the LISA window, and also study the cosmological phase transition and non-perturbative dark matter processes for the production that may be left as signatures in the stochastic gravitational wave background. So as for environmental effects, whenever you have dark matter around a very dense and strong gravity environment, like a black hole or a neutron star, there might be effects that alter the gravitational wave induced signal, for example, in a merger of two compact objects. This is the case for cold dark matter, which can lead to very steep accretion profiles around intermediate mass black holes, and this can induce a dephasing of the gravitational wave form that can be eventually be looked for in current data. And on the other hand, also very light boson fields can form boson clouds gravitationally bounded states around black holes and lead to the phenomenon of superradiance, which can not only slow down black hole spins, so that can be studied with accumulating enough statistics about the spins of black holes, but can also induce gravitational waves, which can then fall either in the LIGO or LISA bands. So to conclude, I hope I conveyed the message that indirect searches has been really successfully to test the different dark matter models, so not only WIMPs candidates, but also axion-like particles and primordial black holes, and is now probing a large portion of their parameter space. From indirect detection, we get very strong constraints, but assessing their robustness is crucial, especially when you want to cross-check signal ins. And this is the case, for example, about the origin of some long-standing excesses where the dark matter interpretation is challenged by astrophysical alternatives and can be actually probed by multi-wavelength observation. And the future is bright because we have great experimental progress in the future that will really provide access to yet uncharted portions of the dark matter perimeter space, and we hope to have new windows of opportunity for dark matter detection. So I thank you for the attention, and I'm happy to take your questions.
Okay, thank you also for this very nice review on indirect detection. There is a question which says, can you comment on the results from high-energy neutrinos obtained by IceCube and Antares for WIMP annihilation in the Sun or the galactic center?
Yes, so neutrinos also offer a way to probe actually two different types of interactions. So you can use the neutrinos captured from the Sun and the galactic center actually to set the constraints on the spin dependent elastic cross-section, which is completely complementary to direct detection searches, and actually even more powerful for a range of masses. So for sure, neutrinos offer a unique way to probe this type of process. And I would also like to mention that neutrinos, as seen by IceCube, can also be used to set strong constraints on decaying dark matter. And there were dedicated talks in some parallel sessions.
Mm-hmm. Thank you. I have a question. I mean, is now then clear that all these excesses have an astrophysical origin, like, for example, the excess from the galactic center or the 3.5 keV line and so on?
So no, I mean, it's not clear at all. I can briefly comment on the galactic center excess. For the 3.5 keV line, I think things are even more complicated. But for the galactic center excess, there are actually few independent analyses that points towards a stellar origin, at least partially, of the excess emission, but there is not yet the identification of those sub-threshold point sources that would be responsible for the emission. And so what it would be really needed to actually corroborate these findings is to find those sources which would be very faint, and the best way to do that is to look for them with the radio telescope, and this is something that is in the current effort of the community. Not sure if I have answered completely.
So you mentioned that the TV range is very well covered, no? Or will be covered in the future with CTA, for example. But you also mentioned that the MeV range is really problematic, no? Because there is no any experiment still going on or that will be working in the future, no? So what will happen with that region?
Yes, so I think there is really all the interest of the scientific community in trying to push for this type of missions. It's already quite some year that people are proposing those either at ESA and NASA, but those have not been funded yet. So I think we still have to try to push and to collect also a larger and broader mass, critical mass, to be able to have those being funded, because this would be really push down and open completely new perspective on the high energy sky, that either from both from the point of view of the astrophysical mechanisms and for dark matter as well. Mm-hmm. So people are still working on this and will do so in the future. So hopefully this will be funded at a certain point.
Unfortunately, in the far future, no, because these missions take a long time to
Yes, and there's plenty of proposal. I invite you all who are interested in that to look at the ICRC proceedings because there were different instruments proposed and could be of interest for the whole community.
Okay, thank you very much. If there are no more questions, we are basically on time, 3:30. So thank you again for this very nice review. And well, now I think we have to close the session, and then everybody will have to reconnect at 4 for continue with the next session. Okay. So thank you to all of you. Thank you to both speakers, and see you later. Bye.